Good morning. Today we are going to discuss about Laplace transform. So in previous sessions we have a discussion about Fourier transforms, and Laplace transform is a similar integral transform. And today we are going to the theoretical background of Laplace transform, just with how we define Laplace transform and some preliminary theorems which we are going to use in Laplace transforms, etc. And after that, we will move on to uh, the concept of the move on to problem solving session, in which we cover a number of problems and some applications of Laplace transform. So, we start with Laplace transform, the definition of Laplace transform. And before that, we have the following prerequisites: the fundamentals of calculus and some knowledge about differential equations and initial value problems. Hope you all have an idea about integral calculus and differential calculus, and what do you mean by differential equation, and what is an initial value problem. Now, the definition of Laplace transform. So here we consider a real valued function f of t. The independent variable is t. It's a convention. Instead of writing f of x, we write f of t. That's because most of the applications of Laplace transforms are in a field which is related to a function in which the independent variable is time. So anyhow, f of t is a real valued function defined for all values of t which is greater than 0. Then the Laplace transform is given by f of s is equal to capital F of s is equal to integral 0 to infinity e raised to minus st into f of t dt. So look at the similarity between Fourier transform and Laplace transform. So it is integral 0 to infinity e raised to minus st into f of t dt. So it is an integral transform. We multiply the function f of t with a kernel, then integrate it in between the limits. And in that case, if capital F of s is the Laplace transform of f of t, then we write as f of t is equal to L inverse of capital F of s. The inverse Laplace transform of capital F of s is f of t. So remember one thing, in Fourier transform we have a clear-cut formula to find the inverse Fourier transform, but in the case of Laplace transform, we don't have any such, we are not going to use any such simple formula to find the inverse Laplace transform. What we are going to do is this one-to-one correspondence. If capital F of s is the Laplace transform of f of t, then f of t is the inverse Laplace transform of capital F of s. This will be clear when we deal with some numerical problems. So here some basic theorems. First one, the Laplace transform is a linear transform. Being an integral transform, it is linear. And the second thing, it's the theorem is known as first shifting theorem, which will help to find the Laplace transform of many functions. It gives Laplace transform of e raised to at into f of t. If f of t is a function which has a Laplace transform capital F of s, then the Laplace transform of a function which is obtained by multiplying f of t with e raised to at is given by capital F of s minus a. That is, we replace s with s minus a. Then in such a case, the inverse Laplace transform of f of s minus a is equal to e raised to at into f of t. All these theorems are going to utilize in while we are dealing with problems. Now, if f of t is a function with the Laplace transform capital F of s, then t into f of t has the Laplace transform minus d by ds of f of s. So if we multiply a function with t, then its Laplace transform can be obtained by differentiating capital F of s with respect to s uh, with a negative sign. Now that result can be extended anyway, and if we divide a function f of t by t, then its Laplace transform is given by s to infinity f of s ds. And uh, the Laplace transform of derivative of functions. If f of t is a function with Laplace transform capital F of s, then uh, the Laplace transform of f dash, the first derivative of f, is given by s into Laplace transform of f minus f of 0, and Laplace transform of f2 dash is equal to s square into L of f minus s into f of 0 minus f dash 0. So in these expressions, if we have the Laplace transform of f and the value of f at 0 and f dash at 0, then we can calculate the Laplace transform of f dash, f2 dash, etc. And this result can be extended to any integer n. So this theorem is going to be used in solving linear differential equations using Laplace transform. So this is an important result. And now the Laplace transform of integrals. If we have an expression for Laplace transform of derivatives, then what about integrals? The Laplace transform of integrals is given by Laplace transform of integral 0 to t f of tau d tau is equal to 1 by s into f of s. So that's the method by which we can calculate the Laplace transform of integrals. This is also useful, and now we define an interesting concept of unit step function or Heaviside function, which is defined as u of t minus a is equal to 0 if t is less than a and is equal to 1 if t is greater than a. Um, so it's a simple function which make a unit increment at the point a. Before a it is 0, after a it is equal to 1. And if we have an arbitrary function f of t, then we can shift the function f of t using the unit step function as f of t minus a into u of t minus a, which is usually denoted as f tilde of t, which is known as the shifted function, and it is equal to 0 when t is less than a and equal to f of t minus a if t is greater than a. We will illustrate the concept of unit step function and shifting of an arbitrary function using some examples when we are dealing with problems. Then in that case, uh, the Laplace transform of the shifted function can be obtained by just multiplying f of s with e raised to minus as. So the Laplace transform of f tilde of t is equal to e raised to minus as into f of s. And while we are looking for the inverse Laplace transform of some functions of the form e raised to minus as into f of s, where f of s is the Laplace transform of f of t, then the inverse Laplace transform is given by f of t minus a into u of t minus a. The result given in equation number 15 is very much important. That result can be useful in solving problems. Then here we have the concept of convolution of two functions. If f and g are two real valued functions, f of t and g of t, then the convolution of f and g is defined as f star g of t is equal to integral 0 to t f of tau into g of t minus tau dt is a new function or new operation between two functions. Then we are looking for the Laplace transform of convolution of functions, or how we can relate the convolution of function to Laplace transform, and the same thing is going to be discussed in Fourier transforms also. So here we have the convolution theorem. If we have two functions f and g with the Laplace transforms capital F and capital G respectively, then the transform of f star g of t, that is convolution of f and g, is the product of capital F and capital G. So the Laplace transform of convolution of two functions is equal to the product of Laplace transforms. So we already discussed that Laplace transform of sum of two functions is equal to sum of Laplace transforms. Laplace transform is a linear transformation. But when we discuss about product of two functions, this is the result which we have. The if f and g are two functions, then the Laplace transform of convolution of two functions is equal to the Laplace transform of the product of Laplace transforms of those functions. And the second result, that is given in equation number 18, Laplace inverse of capital F into capital G. Laplace inverse of product of two functions in S is equal to the convolution of small f and small g. This is again a useful result. Now we are not going into much examples now. We just illustrate, or we just give simple examples of how we can come up with the Laplace transform of some simple functions. More examples will be discussed later. So if you are looking for the Laplace transform of 1, f of x or f of t is equal to 1, then it's equal to integral 0 to t 1 into e raised to minus st dt, that's the definition. Then the integral e raised to minus st, the integral is minus e raised to minus st by minus s in between 0 and infinity. At infinity, e raised to minus st, e raised to minus s into infinity, e raised to minus infinity is 0, and at lower bound it is e raised to 0, that is 1, and so it is 0 minus 1, that is minus 1 by minus s, that is 1 by s. So the Laplace transform of 1 is equal to 1 by s. So how we approach this result? Usually when we are looking for the Laplace transform of 1, Laplace transform of 1 is 1 by s, and if you have an expression capital F of s is equal to 1 by s, then its inverse Laplace transform is 1. So that is how we relate Laplace transform, or the function and its Laplace transform. Or we can find the inverse transform. Say maybe if we tabulate all the functions and its Laplace transforms, then from that table we can find the inverse transform of expressions. So if you look at the table, then we can find 1 by s is the Laplace transform of 1, and therefore 1 by s, the inverse Laplace transform is 1. Now if we calculate the Laplace transform of t, then integral 0 to infinity t into e raised to minus st dt, then using product rule, first function t into integral of e raised to minus st, that is e raised to minus st divided by minus s, minus derivative of derivative of t, that is 1 into integral of derivative of the first, and so on. So it is e raised to minus st divided by minus s into minus s, that is plus s square. Now the limit is 0 to infinity. Then applying the limit, we can have the value as 1 by s square. So the Laplace transform of t is 1 by s square. So the inverse Laplace transform of 1 by s square is t. So that's the relation. Inverse Laplace transform of 1 by s is 1. Inverse Laplace transform of 1 by s square is t. Now, um, we can have a general formula. Laplace transform of t raised n is equal to n factorial divided by s raised n plus 1. N factorial divided by s raised n plus 1. So if you have some t cube, then the Laplace transform is 3 factorial divided by s raised to 4. S raised to 3 plus 1, that is s raised to 4. So that is 6 by s raised to 4. And this one can be again used to calculate the inverse Laplace transform of some functions of the form 1 by s raised to n or s raised to n plus 1. So if you have an expression like 1 by s square or 1 by s cube or 1 by s raised to 4, then we can use this result to find out the inverse Laplace transform. 1 by s raised to n plus 1 has the inverse Laplace transform as t raised to n by n factorial. Then another general example is the Laplace transform of e raised to at, the exponential function. So just using the definition, it is integral 0 to infinity e raised to at into e raised to minus at dt. So it is 0 to infinity e raised to minus of s minus a into t dt. Then is integral is e raised to minus of s minus a into t divided by minus of s minus a in between 0 and infinity. Applying the upper limit and lower limit, we have the value is equal to 1 by s minus a. So the Laplace transform of e raised to at is equal to 1 by s minus a, and in other words, the inverse Laplace transform of 1 by s minus a is equal to e raised to at. So the inverse Laplace transform of 1 by s minus 1 is equal to e raised to t, 1 by s minus 5 is equal to e raised to 5t, 1 by s plus 3 is equal to e raised to minus 3t, and so on. So uh, so for the time being, we are just stopping here, and we will uh, meet again with a number of problems, numerical problems or examples. And for the time being, stop here. Thank you.